somewhere out in the dark, about 26,000 light years from where you are lying right now, there is a star so massive it could swallow our entire solar system whole. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. That star is not special, not by the standards of the universe. There are an estimated 200 billion trillion stars spread across the observable universe. That is a 2 followed by 23 zeros. And most of them are quietly doing the same thing. Burning, holding themselves together through a constant, ancient tug of war between two enormous forces. Take a slow breath and picture it. A star is, at its heart, a giant ball of gas. Mostly hydrogen, the simplest, lightest element there is. Gravity pulls all of that gas inward, squeezing it tighter and tighter toward the center. Left alone, that pressure would crush the star into nothing. But something pushes back, deep in the core, where the pressure and heat become almost impossible to imagine. Hydrogen atoms are forced so close together that they fuse, they merge, and release an enormous flood of energy. That energy pushes outward. Gravity pulls inward, and for millions, sometimes billions of years, those two forces hold each other in perfect balance. That balance is a star. Our own sun has been holding that balance for about 4.5 billion years. It sits at the center of our solar system, roughly 93 million miles from Earth. And it is so large that about 1 million Earths could fit inside it. And yet, by the standards of the universe, our sun is considered average, a quiet, middle-sized star living a calm, ordinary life. Other stars are far more extreme. Some stars are called red dwarfs, small, cool, dim stars that burn their fuel so slowly they can live for trillions of years. The universe itself is only about 13.8 billion years old, which means not a single red dwarf has ever had enough time to die. They are still out there, glowing faintly, patient beyond all measure. Then there are the giants. Stars 10, 20, 50, even 100 times more massive than our sun. These stars burn hot and bright and fast. They are blue-white in color, blazing with a fierce, electric light. Where our sun burns, at about 10,000 degrees Fahrenheit at its surface. The hottest massive stars can reach over 70,000 degrees. They are extravagant with their fuel. They spend it quickly, and because of that, they do not live long, not by cosmic standards. A star 40 times the mass of our sun might live only a few million years before it reaches a crisis point. That crisis is what this entire episode is about. But before we get there, it helps to understand just how much a star contains. The sun, for example, holds more than 99% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, all of it combined makes up less than 1% of what the sun holds. Stars are not just large. They are the dominant objects in the universe. They are the engines that drive everything around them. And they are not silent. Scientists have discovered that stars vibrate. They ring like enormous bells, producing waves of pressure that move through their interiors. This field of study is called astrososmology, the science of listening to the inner life of stars. By studying these vibrations, scientists can learn what is happening deep inside a star, in places no light can ever escape from. It is a little like pressing your ear to the side of something vast and hearing it breathe. Every star you see in the night sky is a sun. Some are larger than ours. Some are smaller. Some are already dead, and the light you are seeing left them thousands of years ago, crossing the dark between galaxies just to reach your eyes tonight. The universe is so large that even light, the fastest thing that exists, takes time to cross it. And somewhere in all of that dark and distance, massive stars are quietly running out of time. Their cores are shifting. Their fuel is changing. The balance that has held them together for millions of years is beginning to tip. When it does, the result is one of the most powerful events the universe is capable of producing. We call it a supernova. A star lives a long life before it dies. Most stars burn for millions or even billions of years. Our own sun has been burning for about 4.5 billion years, and scientists believe it has roughly another 5 billion years left. That is a span of time so large it is almost impossible to hold in your mind. If the entire life of our sun were compressed into a single day, all of human history would fit into the last fraction of a second before midnight. Stars are not made of fire the way a candle is. They are made of plasma, a state of matter so hot that atoms are torn apart, their electrons stripped away and sent flying free. The main ingredient is hydrogen, the simplest and most common element in the universe. A star is essentially a massive ball of hydrogen, held together by its own gravity, constantly burning at its core. The sun contains so much hydrogen that it could fit more than 1 million Earths inside it and still have room. At the center of a star, the pressure is almost unimaginable. Gravity pulls all that mass inward, squeezing the core so tightly that hydrogen atoms are forced to fuse together. This process is called nuclear fusion. When two hydrogen atoms fuse, they form a new, heavier element called helium, and they release a tremendous burst of energy. That energy pushes outward against the force of gravity pulling inward. This tug of war between gravity and energy is what keeps a star alive. It is a balance that can last for an extraordinary amount of time. The size of a star determines how long it lives. Smaller stars burn slowly and carefully, like a candle sheltered from the wind. Our sun is a medium-sized star, and it burns at a steady, measured pace. But the massive stars, the ones 10, 20, even 50 times heavier than our sun, burn through their fuel at a furious rate. A star 30 times the mass of our sun might live for only a few million years before its fuel begins to run out. In cosmic terms, that is a brief life. The Earth itself is older than many of these giant stars ever get to be. These massive stars are also enormous in size. Some of the largest known stars, called red supergiants, are so wide that if you placed one at the center of our solar system, its outer edge would reach past the orbit of Jupiter. Jupiter orbits the Sun at a distance of about 5 times the distance from Earth to the Sun. Picture that. A single star so large it would swallow every inner planet and stretch nearly to the outer solar system. Our Sun, by comparison, would fit inside one of these giants more than 1 billion times over. And yet, despite their size, these massive stars are not the most common kind. Most stars in the universe are small, dim, and cool, called red dwarfs. They are so efficient with their fuel that some of them may burn for trillions of years. The universe itself is only about 13.8 billion years old, which means the oldest red dwarfs have barely begun their lives. They will still be burning long after every massive star alive today has exploded and gone dark. The light a star produces depends on its temperature. Cooler stars glow red or orange. Hotter stars burn white or blue. Our sun burns yellow-white with a surface temperature of about 5,500 degrees Celsius. The hottest massive stars burn blue with surface temperatures that can reach 40,000 degrees or more. When you look up at the night sky and notice that some stars look slightly different in color, you are seeing real differences in temperature, size, and age. The night sky is not a flat backdrop. It is a crowd of individual suns, each at its own stage of life. For most of a star's life, nothing dramatic happens. It simply burns. Hydrogen fuses into helium, energy flows outward, and the star holds its shape. Millions of years pass. Hundreds of millions. The star sits in its place in the galaxy, steady and bright, warming whatever orbits around it. It looks permanent. It feels permanent. But deep inside, the hydrogen is slowly being used up. The core is filling with helium, like ash collecting at the bottom of a fire. The star does not notice, not yet. It keeps burning. It keeps shining. But the balance that has held it together for so long is quietly, gradually, beginning to change. Helium does not burn the same way hydrogen does. Not at first. For a long time, the helium that builds up in the core just sits there, inert and heavy, collecting in the center of the star like a growing weight. The star is still producing energy from the hydrogen burning in the layers around that core. But the core itself has gone quiet. It is no longer contributing. And slowly, that changes everything. Gravity never stops pulling. It is patient in a way that nothing else in the universe is. While the star was fusing hydrogen, the outward push of that energy-balanced gravities inward pull perfectly. That balance is called hydrostatic equilibrium, the state where a star's own energy holds it up against its own weight. For most of a star's life, that balance is nearly perfect. But once the hydrogen in the core runs out, gravity begins to win. The core starts to contract. It squeezes inward, slowly at first, then faster. As the core contracts, something interesting happens. The squeezing generates heat. The core grows hotter than it has ever been. And eventually, if the star is massive enough, that heat reaches a new threshold. The temperature climbs high enough to ignite the helium. Helium begins to fuse into carbon and oxygen. A new fire has started, deeper and hotter than the one before. The star has found a second source of fuel. But this one will not last nearly as long. Meanwhile, the outer layers of the star respond to all of this in a dramatic way. As the core heats up and the energy output changes, those outer layers begin to expand. They swell outward, growing enormous. The star's surface cools as it stretches, and its color shifts from white or yellow toward orange and red. The star has become what astronomers call a red giant, a star that has expanded to many times its original size. Our own sun will do this one day. Scientists estimate that in about 5 billion years, the sun will expand into a red giant large enough to swallow Mercury and Venus, and possibly reach the orbit of Earth. For a massive star, this process moves faster and goes further, much further. A star many times more massive than our sun does not just become a red giant. It becomes a red supergiant, one of the largest objects in the known universe. The star Betelgeuse, which sits at the shoulder of the constellation Orion, is a red supergiant. If Betelgeuse were placed at the center of our solar system, its surface would extend past the orbit of Jupiter. That is how large these stars become. What was once a compact, furiously burning core of hydrogen has grown into something almost too large to picture. But size does not mean stability. Inside the red supergiant, the burning continues through a series of stages, each one shorter than the last. After helium fuses into carbon and oxygen, the carbon can begin to fuse as well, producing neon and magnesium. Then neon neon fuses. Then oxygen. Each stage requires higher temperatures and higher pressures than the one before. Each stage produces less energy and lasts for a shorter time. Hydrogen burning might last millions of years. Helium burning lasts hundreds of thousands. Carbon burning lasts only a few thousand years. Neon burning lasts about a year. Oxygen burning lasts a few months. The star is burning through its options one by one, like a fire working its way through smaller and smaller pieces of wood. And all of this is happening in the core, hidden from view, invisible from the outside. To anyone watching from a distant planet, the star still looks like a star. It still shines. It still holds its shape. The catastrophe building inside it leaves no visible trace. Not yet. Each new fuel produces a new layer of ash. The core develops a layered structure, like the rings of an onion. Hydrogen burns in the outermost shell. Below that, helium burns. Below that, carbon. Then neon. Then oxygen. And at the very center, the heaviest ash of all begins to accumulate. That ash is iron, and iron is where everything changes. Iron is where the long life of a massive star finally meets its end. It cannot be fused to release energy. It only absorbs it. The moment an iron core begins to grow at the heart of a massive star, a clock has started. The star does not know it yet. It keeps burning in its outer shells, steady and bright from the outside. But the end is no longer distant. It is close. It is, in the scale of a star's life, almost here. The iron core grows slowly at first. It builds grain by grain, in the way that sand collects at the bottom of a glass. Each moment of fusion in the shells above adds more iron to the pile below. And unlike every fuel that came before it, iron gives nothing back. Silicon burned and made iron. Oxygen burned and made iron. Every step up the chain of elements produced energy that kept the star alive. But iron is the end of that chain. It sits at the bottom of a deep energy valley, and there is nowhere lower to fall. Scientists call this the Iron Peak. It is the point on the chart of all elements where fusion stops releasing energy and starts consuming it. Iron is, in a sense, the most stable thing in the universe. Its nucleus holds together so tightly that forcing it to fuse with anything else costs more energy than it produces. The star has spent millions of years climbing toward this moment, and now it has arrived. The iron core keeps growing. It cannot stop. The shells above are still burning, still fusing, still raining new iron down onto the pile. A massive star in its final hours might be producing iron at a rate that would seem impossible to imagine. In just the last day of its life, the core can grow to a mass greater than our entire sun. All of that iron packed into a sphere roughly the size of Earth. Dense, dark, and utterly unable to burn. For a long time, the core holds itself up through a kind of pressure that has nothing to do with heat or fire. Electrons, the tiny particles that orbit the center of every atom, resist being pushed together. They push back against the weight of the star above them. This resistance is called electron degeneracy pressure, and it is a real and powerful force. It has held up the cores of smaller dying stars for billions of years, but there is a limit to how much weight it can bear. That limit has a name. Scientists call it the Chandrasekhar limit, after the astronomer Subrahmanyan Chandrasekhar, who calculated it in the 1930s. He was a young man on a ship crossing the ocean when he worked it out. The limit sits at roughly 1, and 4/10 times the mass of our sun. When an iron core crosses that threshold, electron pressure is no longer enough. The core has become too heavy for anything to hold up. What comes next happens with a speed that is almost impossible to describe. But before that moment arrives, something quieter happens. Something that most people never think about. In the final hours before collapse, the star is still layered, still burning in its shells, still shining from the outside. And inside those layers, the elements that make up the known universe are sitting in rings, sorted by weight and temperature. Hydrogen on the outside, helium below that, carbon, neon, oxygen, and silicon in their own bands, and iron at the center. These are not abstract chemicals. They are the same elements that built the world you live on. The oxygen in the air you breathe right now was forged inside a star. The carbon in every living cell on Earth was made in the heart of a dying sun. The calcium in your bones, the nitrogen in your muscles, the sulfur in your skin, all of it was cooked inside stars that lived and died long before our solar system existed. A dying star in its final hours carries within it the raw ingredients for oceans, mountains, forests, and people. The iron at the core is perhaps the most personal of all. Earth has an iron core of its own. It is what generates our planet's magnetic field, the invisible shield that deflects harmful radiation from the sun and makes life possible on the surface. That iron did not come from our sun. Our sun is not massive enough to fuse iron. The iron in Earth's core was forged inside a star far larger than ours. A star that exploded long ago and scattered its contents across space. Those scattered elements eventually gathered into the cloud that formed our solar system. The iron sank to the center of our young planet and has been there ever since. So, in a very real sense, the iron core of a dying star and the iron core of our living Earth are connected across billions of years and billions of miles. The star does not know what it is building. It only burns and collapses and gives. And in its final hours, it holds within it the seeds of everything that will come after. And now the giving begins. In those final hours, the iron core sits at the center of the dying star like a stone at the bottom of a deep lake. It cannot burn. It cannot fuse. Iron is the end of the line for nuclear fusion, the point where no more energy can be squeezed out by pressing atoms together. So the core simply sits there, growing heavier as more iron rains down from the layers above. And all the while, gravity is waiting. Gravity never stops. It never tires. For millions of years, the outward push of nuclear burning held gravity in check. The star was a constant tug-of-war between two enormous forces, the pressure of fusion pushing out and the weight of all that gas pushing in. For most of a star's life, those two forces stay balanced. The star holds its shape. It shines steadily. It seems permanent, even though nothing is permanent. But when the iron core can no longer produce energy, the outward push weakens, and gravity wins. What happens next takes less than 1 second. In that single second the iron core, which at this point is roughly the size of Earth, but contains more mass than our entire sun, collapses inward. It does not crumble slowly. It falls. The outer edge of the core plunges toward the center at roughly 1/4 the speed of light. That is about 45,000 miles per second. The collapse is so fast that the star's outer layers have no time to react. They do not yet know the core is gone. As the core falls inward, the pressure inside it becomes almost impossible to imagine. Electrons, the tiny particles that orbit the center of every atom, get forced into the atomic nuclei themselves. They merge with protons there, creating particles called neutrons. This process releases enormous amounts of energy in the form of neutrinos, which are tiny, nearly massless particles that barely interact with anything at all. Under normal conditions, a neutrino could pass through a wall of solid, lead 1 light-year thick, and never touch a single atom. They are the most ghostly things in the universe. But inside a collapsing stellar core, the density becomes so extreme that even neutrinos are briefly trapped. The core becomes a neutron star in the making, a sphere perhaps 12 miles across, packed with more matter than the sun, squeezed so tightly that a single teaspoon of it would weigh about 1 billion tons. The core has become one of the densest objects the universe is capable of producing. And then something extraordinary happens. The collapsing core reaches a limit. Neutrons resist being compressed any further. There is a quantum mechanical force, a rule written into the fabric of matter itself, that says neutrons cannot be pushed into the same space as other neutrons. Scientists call this neutron degeneracy pressure. The core stiffens suddenly, like hitting concrete after a long fall. It bounces. That bounce sends a shockwave outward. A shockwave is a wave of pressure, like the ripple from a stone dropped into still water, but almost unimaginably more powerful. This shockwave begins to travel outward through the star at tremendous speed. It carries the energy of the collapse with it, and it is heading toward the star's outer layers, which have been falling inward this whole time, still unaware of what has happened below. The shockwave and the infalling outer layers meet. For a brief moment, the shockwave stalls. it loses energy fighting against all that mass falling inward. Scientists have spent decades trying to understand exactly how the shockwave recovers, how it gathers enough strength to keep moving. The answer seems to involve those ghostly neutrinos, even though neutrinos barely interact with matter. There are so many of them pouring out of the collapsing core that a small fraction of them are absorbed by the stalled shockwave. That tiny fraction carries enough energy to revive it. Neutrinos, particles so small and shy that they pass through the entire Earth without slowing down, are what save the shockwave. They are what allow the explosion to happen at all. It is one of the quieter wonders of physics. The most violent event in the known universe depends on the gentlest of particles. The shockwave gathers itself. It begins to move outward again, gaining speed, carrying heat and pressure and light. The star's outer layers, still falling inward, suddenly find themselves in the path of something they cannot stop. The forces that held the star together for millions of years are about to be undone in a matter of minutes. The collapse is nearly complete. The explosion is about to begin. The shockwave moves outward at roughly 30,000 kilometers per second. That is about 1/10 the speed of light. To feel the scale of that number, consider this. A passenger jet travels about 900 kilometers per hour. The shockwave from a collapsing stellar core moves about 120 million times faster than that. It crosses the entire diameter of the Earth in less than the time it takes to blink. And yet, the star it must cross is enormous. A massive star near the end of its life can swell to hundreds of times the size of our own sun. If our sun were placed at the center of our solar system, which it is, a star like Betelgeuse would stretch nearly to the orbit of Jupiter. The shockwave, moving at 1/10 of the speed of light, still takes several hours to reach the outer surface of a star that large, several hours to cross something so vast that our entire inner solar system would fit inside it. That is the scale of what is happening. The shockwave carries an almost impossible amount of energy. In the first second of the explosion, a core collapse supernova releases more energy than our sun will produce in its entire 10 billion year lifetime. Scientists write that number with 44 zeros behind it, measured in a unit called ergs. Numbers that large stop feeling like numbers. They start feeling like something else entirely, like the universe reminding us how quietly enormous it truly is. Most of that energy, around 99%, leaves the star in the form of neutrinos. Those same ghostly particles that revived the stalled shockwave now pour outward in a flood so dense that, for a brief moment, even the near-empty space around the dying star becomes thick with them, a single cubic centimeter of space near the explosion. A cube about the size of a sugar cube holds more neutrinos in that instant than the entire Earth will ever encounter from our own sun in millions of years. The remaining 1% of the energy goes into the shockwave itself. 1% sounds small, but 1% of a number with 44 zeros behind it is still a number with 42 zeros behind it. That is the energy that physically tears the star apart. It heats the outer layers to temperatures of billions of degrees. It accelerates gas and plasma outward at speeds that would carry you from Earth to the Moon in less than 15 seconds. As the shockwave pushes through the star's outer layers, it compresses and heats everything in its path. The gas glows. It radiates light across every wavelength: visible light, ultraviolet light, X-rays. The star, which spent millions of years slowly burning, now releases the energy of an entire galaxy's worth of stars in a single brilliant flash. For a short time, one dying star outshines every other star in its galaxy combined. Billions of stars, dimmed to nothing by the light of one. The outer layers of the star, some of which were fusing lighter elements like hydrogen and helium, right up until the final moments, get swept up in the shockwave and flung outward. They do not drift. They are hurled. The ejected material, called the stellar envelope, can travel at 10,000 kilometers per second, even after the initial blast has passed. That is fast enough to cross the distance between Earth and the Moon in less than 40 seconds. All of this happens in a star that, from our distance, looks like a single quiet point of light. The Sun, our own star, sits about 150 million kilometers away. At that distance, it looks like a blazing disk in the sky. A supernova in a nearby galaxy can be tens of thousands of light years away. 1 light year alone is about 9.5 trillion kilometers. And yet, it still blazes bright enough to see without a telescope. The sheer output of energy involved is difficult to hold in the mind. It is easier to simply sit with it, to let the numbers wash over you like the light from a distant shore. The shockwave is still moving. It will not stop at the edge of the star. It will push outward into the space surrounding the explosion, carrying with it all the material the star spent millions of years building. Layers of carbon, oxygen, neon, silicon, and iron. All the elements forged in the long, slow burn of a stellar life now scatter into the dark. The star is gone, but what it made is just beginning to travel. That light begins its journey the moment the star tears itself apart. A supernova does not simply flash and vanish. In the first hours after the explosion, the expanding shell of gas and energy glows with a brightness that can outshine every other star in its entire galaxy combined. Picture that for a moment. A single dying star pouring out more light than hundreds of billions of stars, all burning at once. The galaxy around it dims by comparison, like a single candle next to the sun. But what does that light actually look like as it travels toward us? When the shockwave first breaks through the outer surface of the star, it releases a burst of ultraviolet light and X-rays so intense that no human eye could survive looking at it directly, even from an enormous distance. This initial flash is called shock breakout, and it lasts only minutes. Scientists have only caught this flash a handful of times because it happens so fast and without warning. To see one is an extraordinary stroke of luck. Telescopes must simply be pointed in the right direction at exactly the right moment. After that first blinding pulse, the supernova settles into something more sustained. The expanding cloud of gas and debris heats up as it moves outward. It glows. The colors shift over days and weeks, moving from a fierce blue-white at the hottest temperatures toward yellow, then orange, then deep red as the gas cools. If you could float in space at a safe distance and watch this unfold, it would look something like a slow sunrise that never quite ends. A bloom of light spreading across the dark, changing color as it breathes outward. The light we see from a supernova does not all come from the same source. Some of it comes from the raw heat of the explosion itself, but a large portion comes from something else entirely. As the star explodes, it forges a radioactive element called nickel-56 deep inside the blast. This nickel decays, meaning it breaks down into other elements over time. First, it becomes cobalt-56, then stable iron. Each step in that decay releases energy, and that energy powers the glow of the supernova for weeks and months after the initial blast. The light we see in the night sky is partly the slow, steady release of energy from atoms changing their very nature. This is why a supernova does not simply flash and go dark. It fades gradually, like an ember cooling after a fire. The brightness peaks, then slowly dims over a curve that astronomers can measure and predict. That curve, called the light curve, is one of the most useful tools in all of astronomy. By watching how a supernova brightens and fades, scientists can calculate how far away it is, how much nickel was produced, and what kind of star exploded in the first place. The light also carries information hidden inside it. When astronomers split that light apart using an instrument called a spectrograph, they can read the chemical fingerprints of every element present in the explosion. Each element absorbs and emits light at specific wavelengths, leaving a pattern as unique as a signature. Iron looks different from oxygen. Silicon looks different from calcium. By reading these patterns, scientists can reconstruct the entire history of what the star was made of and what it created in its final moments. Light from a distant supernova can take millions of years to reach us. When it finally arrives, it carries a message from an event that happened long before our sun even existed. The photons, the tiny particles of light, travel in a straight line across the expanding universe. They pass through clouds of gas. They bend slightly around massive objects. They stretch as the universe itself grows larger, shifting toward the red end of the spectrum in a process called redshift. by the time they reach our eyes or our telescopes, they have traveled farther than almost anything else we can observe. And yet they arrive. They land on our instruments. They leave a signal we can read. There is something deeply quiet about that. A star lived for millions of years. It burned and fused and finally collapsed. It sent out a pulse of light in every direction. And some of that light, after crossing an almost unimaginable distance, found its way here, found its way to a small blue planet orbiting an ordinary star in one arm of a spiral galaxy, found its way to a telescope or a human eye looking up on a clear night. The light does not know it has arrived, but we do. And that small fact, that we can receive these ancient messages at all, is one of the quieter wonders of living in this universe. When a supernova's light finally reaches Earth, it does not arrive all at once. It comes in layers. First, the neutrinos, tiny, nearly massless particles that barely interact with anything, slip through the explosion and race ahead of the light itself. They travel so fast and so freely that they arrive at Earth hours before the visible glow does. This is not a guess. We have seen it happen. In 1987, detectors buried deep underground caught a burst of neutrinos from a dying star in a nearby galaxy. Those detectors registered the signal roughly 3 hours before anyone saw the star brighten in the sky. The neutrinos arrived first, quiet and invisible, like a whisper before the thunder. Those underground detectors were not built to watch for supernovae. They were built to study neutrinos for other reasons entirely. But the universe does not wait for us to be ready. When the star called Sanjulik, a blue supergiant sitting in the large Magellanic Cloud, about 168,000 light years away, collapsed and exploded. The neutrinos it released passed right through the planet. Most of them passed through every human body on Earth without stopping. Only a handful were caught. Just 24 neutrinos detected across 3 separate underground facilities around the world. 24 particles out of the vast flood the dying star released. And those 24 were enough to confirm what physicists had long predicted about how a massive star dies. What followed those neutrinos was light, light arrived, astronomers could watch the supernova brighten over days and weeks. A supernova does not flash and vanish. It rises slowly to a peak, then fades over months. The brightness follows a curve that scientists call a light curve, and that curve carries information. The shape of the rise and fall tells astronomers what kind of star exploded, how much material it threw off, and what elements are glowing in the expanding shell. Reading a light curve is a little like reading a fingerprint. Each supernova leaves its own. The peak brightness of a supernova can be staggering. At its brightest, a supernova can outshine every other star in its entire galaxy combined. The galaxy might contain hundreds of billions of stars, each one burning steadily. And for a few weeks, a single dying star blazes brighter than all of them together. From Earth, a supernova in a distant galaxy appears as a new point of light where none existed before. It looks at first glance like a new star. The word nova comes from the Latin for new. Early astronomers who saw these sudden bright points had no way to know they were watching something die. Closer supernovae, those within our own galaxy, can be visible even in daylight. Historical records describe exactly this. A supernova that exploded in the year 1006 was so bright that people could read by its light at night. It was visible for months. Astronomers in China, Egypt, Iraq, and Switzerland all recorded it. That event left behind a faint glowing shell of gas that we can still detect today with radio telescopes and X-ray instruments. 1,000 years later, still slowly expanding outward through space, modern telescopes do not wait for supernovae to announce themselves. Automated sky surveys scan thousands of galaxies every single night, comparing new images to older ones, looking for any point of light that was not there before. When a new bright spot appears in a galaxy, the software flags it. Astronomers then point more powerful instruments at it within hours. This process has allowed scientists to catch supernovae very early in their brightening, sometimes within a day of the initial explosion. The earlier you catch one, the more you can learn about the moments just after the star collapsed. Some of what we detect does not come as light at all. Supernovae release enormous amounts of energy as X-rays and gamma rays, forms of radiation far more energetic than visible light. Space-based telescopes orbiting above Earth's atmosphere catch these high-energy signals. The atmosphere blocks most X-rays and gamma rays from reaching the ground, which means ground-based observers would miss this part of the story entirely without the help of satellites. Each wavelength of radiation tells a different part of what happened inside the explosion. Visible light, radio waves, X-rays, neutrinos. Together, they build a full picture that no single instrument could assemble alone. This is one of the quieter lessons of modern astronomy. No one tool sees everything. The universe speaks in many frequencies at once. And only by listening across all of them, by combining every signal from every kind of detector, do we begin to understand what a dying star is truly saying. Long before satellites and radio telescopes, before any of the tools we use today, human beings looked up and saw stars explode. They did not know what they were seeing, but they wrote it down. They carved it into stone, painted it on cave walls, recorded it in careful logs kept by royal astronomers. These records survived for centuries, and today, scientists read those ancient accounts and match them to glowing clouds of gas still drifting through the sky. The past and the present speak to each other across 1,000 years. One of the most famous of these events happened in the year 1006. Astronomers in China, Egypt, Iraq, and Switzerland all recorded a new star appearing in the southern sky. It was so bright that people could see it during the day. Some accounts say it cast faint shadows at night. Modern astronomers have since found the remnant, the expanding shell of gas left behind by that explosion, in the constellation Lupus. It sits about 7,200 light-years away. What those ancient skywatchers saw was the brightest supernova recorded in all of human history. Just 48 years later, in 1054, another star exploded. Chinese astronomers called it a guest star. They recorded it carefully, noting its position and its brightness over many months. It was visible in daylight for about 3 weeks. Native American rock art in the American Southwest may also preserve images of this event, painted by people who watched the sky and understood that something remarkable had arrived. What that explosion left behind is what we now call the Crab Nebula, a glowing, tangled cloud of gas about 6,500 light years from Earth. At its center spins a neutron star, the crushed core of the original star, rotating 30 times every second. The Crab Nebula is one of the most studied objects in the sky. Every time astronomers point a new telescope at it, they learn something new. The explosion happened nearly 1,000 years ago, and it is still teaching us. In 1572, a young Danish astronomer named Tycho Brahe stepped outside one November evening and saw something that stopped him cold. A brilliant new star blazed in the constellation Cassiopeia. It was so bright it could be seen in full daylight. Tycho watched it carefully for months and wrote a detailed account. His book about the event was titled De Nova Stella, which means about the new star. This is where the word nova comes from, a word we still use today. Tycho's careful measurements helped prove that this object was far beyond the moon, which challenged the old belief that the heavens never changed. One exploding star helped crack open an entire way of thinking about the universe. Just 32 years later, in 1604, another supernova appeared. This one was observed by the astronomer Johannes Kepler, who tracked it for over a year. It too was visible in daylight. It outshone every planet in the night sky. Kepler's supernova, as it is now called, was the last supernova visible to the naked eye from within our own galaxy. That was over 400 years ago. Astronomers have been waiting for the next one ever since. The wait has not been entirely empty. In 1987, a star exploded in the Large Magellanic Cloud, a small galaxy that orbits our own Milky Way at a distance of about 168,000 light years. This event, known as SN 1987A, was the closest supernova observed since Kepler's in 1604. It was faint compared to the ancient events, not quite bright enough to see easily without a telescope, but it was close enough for scientists to study in extraordinary detail. For the first time, detectors on Earth caught a burst of neutrinos arriving from the explosion, arriving a few hours before the visible light. That tiny detail confirmed something physicists had predicted, but never directly observed. The neutrinos escaped the collapsing core almost instantly, while the light took hours to fight its way out through the surrounding gas. SN 1987A is still expanding today. Astronomers watch it every year as the shockwave pushes outward into the gas around it, lighting up rings of material the original star shed long before it died. These events form a kind of rhythm across human history. A bright new star appears. People look up, startled and amazed. They write down what they see. Centuries pass, and then scientists find the glowing remnant still drifting through space, still carrying the energy of that ancient moment. The explosion ends in seconds, but the record it leaves behind in the sky and in human memory lasts far longer than the star ever did. When a star explodes, it does not simply vanish. It leaves something behind. That something is one of the most beautiful structures in all of astronomy. A supernova remnant, a vast glowing cloud of gas and dust still rushing outward from the place where the star once stood. These remnants grow slowly by human standards, but they are moving fast. The gas expelled in a supernova can travel at speeds of 10,000 kilometers per second or more. That is fast enough to cross the entire Earth in less than a second. And yet, because space is so enormous, a remnant can take tens of thousands of years to fully expand and fade. The Crab Nebula is perhaps the most studied remnant in the sky. It sits about 6,500 light years away in the constellation Taurus. It is the leftover cloud from a supernova that ancient astronomers watched in the year 1054. Today, nearly 1,000 years later, it still glows with a pale blue and red light. It stretches across roughly 11 light years of space, and it is still growing, still pushing outward, still carrying the energy of that single moment of stellar death. When you look at an image of the Crab Nebula, you are not just seeing gas. You are seeing history. The filaments, those long, tangled threads of glowing material, are the actual outer layers of the star that exploded. They were once part of a living sun. Now they drift through space, lit from within by a spinning neutron star at the center, which we will come to soon. Not all remnants look the same. Some form near-perfect spheres, like soap bubbles blown into the dark. Others are twisted and irregular, shaped by the gas and dust the original star shed during its long life before the explosion. The surrounding space is rarely empty. Stars spend thousands of years exhaling material before they die, and that material forms a kind of neighborhood around them. When the shockwave from the explosion hits that surrounding gas, it lights it up. The result can look like glowing rings or shells or rippling curtains of color. Cassiopeia A is another famous remnant. It sits about 11,000 light years away. The star that created it likely exploded sometime around the year 1680, though no clear historical record of the explosion survives. When radio telescopes first detected it in the mid-20th century, scientists were surprised by how bright it was. Cassiopeia A is now one of the strongest sources of radio waves in the entire sky. Its outer shell glows in X-rays, visible light, and radio waves all at once. Scientists have used it to map the temperatures and densities of the gas in ways that reveal exactly how the explosion unfolded, layer by layer. What makes remnants so important is not just their beauty. They are engines of change. As the shockwave from a supernova pushes outward, it compresses the gas it runs into. That compression can trigger new clouds of gas to collapse inward. And collapsing gas clouds are how new stars are born. A supernova remnant drifting through a galaxy can quietly set off a chain of new star formation simply by pushing on the gas around it. Death becomes the pressure that creates new life. The remnant also carries with it all the heavy elements forged in the explosion: iron, calcium, silicon, sulfur. All of it is mixed into the expanding cloud. Over millions of years, that cloud cools and thins. It blends with the gas already floating between the stars. And eventually, some of that enriched gas will find its way into a new collapsing cloud, a new star, and perhaps a new set of planets. The remnant is not just a record of the past. It is a delivery system for the future. Some remnants last only a few thousand years before they fade below what our instruments can detect. Others, under the right conditions, can remain visible for 100,000 years or more. The oldest known remnants are ghostly and faint, barely distinguishable from the surrounding space. But they are there, still spreading, still carrying their ancient energy outward into the dark. Every remnant is a kind of echo. The star is gone, but the space around it has been changed forever. The gas has been heated and stirred. New elements have been scattered across light years. The shockwave has moved on, pressing into new regions of the galaxy, nudging things that will not respond for millions of years. A supernova ends in a moment, but its reach extends across time in ways that are almost impossible to hold in the mind all at once. And yet, for all that a supernova scatters outward, something remains at the center. Something small, something almost impossible to believe. When a massive star collapses, the outer layers explode away. But the core does not always become a black hole. Sometimes it survives. It is crushed down into one of the strangest objects in the known universe. Scientists call it a neutron star. A neutron star is the collapsed heart of a dead star. It is made almost entirely of neutrons, the tiny particles that once lived inside the star's atoms. The explosion stripped everything else away. What is left is a ball of pure, compressed matter, packed together so tightly that normal ideas about density simply stop working. Picture the entire mass of our sun. All of it. Every burning, churning ton of it. Now imagine squeezing that mass into a sphere about the size of a city. A sphere roughly 10 to 15 miles across. That is a neutron star. It is not a metaphor. It is what actually happens. The density of a neutron star is almost beyond language. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. Not 1 billion pounds. 1 billion tons. That one small spoonful would outweigh every mountain range on our planet combined. The matter inside is so compressed that the neutrons themselves are pressed together, touching, with almost no space between them at all. Neutron stars are also extraordinarily hot when they are first born. temperatures at the surface can reach around 1,000,000 degrees Celsius in their early life. The interior is even hotter. Scientists believe the core of a young neutron star may reach temperatures of 100 billion degrees or more in the first seconds after its birth. Over thousands of years, the star slowly cools. But even an old neutron star still glows in X-ray light, radiating heat into the surrounding dark. And they spin. This is one of the most striking things about neutron stars. They spin very, very fast. When a star collapses, it conserves something called angular momentum. Think of a spinning figure skater who pulls their arms inward. They spin faster. A collapsing star does the same thing, but on a scale that is hard to hold in the mind. A star that once rotated slowly, once every few weeks, collapses into something tiny. And that tiny object spins at extraordinary speed. Some neutron stars rotate hundreds of times every single second, not hundreds of times per minute, per second. The surface of such a star is moving at a significant fraction of the speed of light. Neutron stars also carry magnetic fields of staggering strength. The magnetic field of a neutron star can be 1,000,000,000,000 times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger than that. Scientists believe magnetars have the most powerful magnetic fields of any known object in the universe. These fields are so intense that they would affect the very structure of atoms if you were anywhere nearby, which, of course, you would not want to be. The gravity on the surface of a neutron star is roughly 200 billion times stronger than the gravity you feel right now. If you could somehow stand on the surface of a neutron star, which is physically impossible, the gravity would be so strong that even the tiniest motion would require more energy than any human body could ever produce. The escape velocity from a neutron star's surface is roughly half the speed of light. To leave, you would need to be moving at about 150,000 kilometers per second. Neutron stars can also be found in pairs. Two neutron stars can orbit each other, locked together by gravity, circling for millions of years. As they orbit, they slowly lose energy. They spiral inward, closer and closer, and eventually they collide. That collision is one of the most violent events in the universe, but it is also one of the most creative. Scientists have found that neutron star collisions forge some of the heaviest elements in nature, including gold and platinum. The ring on a finger, the clasp on a necklace, may carry atoms born in that kind of collision billions of years ago. A neutron star is the universe at its most extreme. It is the smallest, densest, fastest spinning, most magnetically powerful object that can still be called a star in any sense. It is what remains when almost everything has been stripped away. And in that compressed, spinning, glowing remnant, the universe has found yet another way to be extraordinary. Some neutron stars do something remarkable. They spin so fast that they send out beams of radio waves, sweeping across the sky like the beam of a lighthouse sweeping across dark water. We call these objects pulsars, and they are among the most precise, most quietly astonishing things in the known universe. The name comes from what we observe. From Earth, the beam sweeps past us again and again, like a clock ticking in deep space. Each pulse arrives with stunning regularity. Some pulsars pulse hundreds of times every second. Others pulse once every few seconds. But nearly all of them pulse with a steadiness that rivals the best atomic clocks humans have ever built. Scientists have used pulsars to measure time with extraordinary accuracy because the universe itself made them that way. When a massive star collapses and becomes a neutron star, it carries with it all the spin of the original star. But now that spin is compressed into something the size of a city. The way a spinning skater pulls in their arms and speeds up, the collapsing star speeds up too. This is called the conservation of angular momentum, which means that spinning things spin faster when they shrink. A star that once rotated once a month can become a neutron star that rotates hundreds of times per second. That is the engine behind a pulsar. The beams themselves come from the magnetic poles of the neutron star. Neutron stars carry magnetic fields trillions of times stronger than Earth's. Those fields funnel charged particles toward the poles, and those particles release energy as tight beams of radiation, radio waves, X-rays, sometimes even gamma rays. The beams shoot out from the poles like twin searchlights. And because the magnetic poles are often tilted relative to the spin axis, the beams sweep around as the star rotates. If Earth happens to sit in the path of that sweep, we see a pulse, a steady, rhythmic signal from across the galaxy. The first pulsar ever detected was discovered in 1967 by a young graduate student named Jocelyn Bell Burnell. She noticed a strange, repeating radio signal in her data. It was so regular, so perfectly timed, that her team initially nicknamed it LGM-1. LGM stood for Little Green Men. The signal seemed almost too precise to be natural. Of course, it was natural. It was a pulsar, about 2,000 light years away, spinning about 30 times per second, and sending its beam sweeping past Earth with quiet, mechanical perfection. Bell Burnell's discovery changed astronomy forever. There is a pulsar sitting at the heart of the Crab Nebula, that glowing cloud of gas left behind by a supernova that ancient astronomers watched in the year 1054. That pulsar spins about 30 times per second. It pulses in radio waves, in visible light, in X-rays. It is one of the brightest pulsars in the sky, and it is slowly slowing down, losing energy over thousands of years, its pulses growing fractionally longer with each passing century. Scientists can measure that slowdown with great precision. It tells them how much energy the pulsar is pouring into the surrounding nebula, lighting it up from within. Some pulsars spin even faster. These are called millisecond pulsars, and they rotate hundreds of times every single second. Some spin more than 700 times per second. At that speed, the surface of the neutron star is moving at a significant fraction of the speed of light. Scientists believe these ultra-fast pulsars were once slower, but they had a companion star nearby. Gas from that companion star fell onto the pulsar and spun it up, like pushing a top to keep it going. The companion star gave the pulsar new energy, new speed. Even in death, stars find ways to interact, to change each other, to pass something along. Pulsars also bend space around them. Their gravity is so strong that the radio beams themselves can be bent by the curvature of space-time near the star's surface. Scientists have used this effect to test Einstein's theory of general relativity, the idea that mass bends the fabric of space and time. Pulsars have confirmed those predictions with beautiful precision. A dead star spinning in the dark has helped confirm some of the deepest ideas in all of physics. There is something deeply calming about a pulsar when you sit with it long enough. It is a remnant. It is what is left after the fire, and yet it pulses on, steady and true, sending its signal across thousands of light years. A quiet drum in the dark, a small spinning thing, keeping perfect time at the edge of the galaxy, long after the star that made it is gone. Sometimes two of those quiet drums find each other. Two neutron stars, each one the crushed remains of a massive star, can orbit one another through space. They circle each other slowly at first, then faster and faster over millions of years. As they spiral inward, they send ripples through the fabric of space itself. These ripples are called gravitational waves, and they carry energy away from the pair, pulling the two stars closer with every orbit. The spiral tightens, the dance accelerates, and then, after perhaps 1 billion years of circling, the two neutron stars finally collide. What happens in that moment is almost beyond imagining. The collision releases more energy in a fraction of a second than our sun will produce in its entire 10 billion year life. A brilliant flash of light erupts across the universe. Heavy elements, forged in the crushing heat of the merger, are flung outward into space. Gold, platinum, silver, the rarest metals in the universe, are born in these brief, violent meetings between dead stars. For a long time, scientists suspected this was happening. The math pointed to it. The physics demanded it. But no one had ever seen it directly. Then came the year 2017, and everything changed. On August 17th of that year, a detector called LIGO, the Laser Interferometer Gravitational Wave Observatory, felt something. LIGO is an extraordinary machine. It uses laser beams and mirrors to measure changes in distance smaller than 1/10,000th the width of a proton. It was built to detect gravitational waves, those tiny ripples in space that Einstein had predicted over 100 years earlier. For most of its history, LIGO had been searching, waiting, listening for a signal in the deep silence. That August morning, the signal arrived. Gravitational waves from two colliding neutron stars washed over Earth, stretching and squeezing space by an almost unimaginably small amount. LIGO caught it. So did its partner detector in Italy, called Virgo. The two observatories together could triangulate where in the sky the signal had come from. Within seconds, astronomers around the world were alerted. Telescopes swung toward a galaxy called NGC 4993, about 130 million light years away. And there it was, a bright point of light that had not been there before. A kilonova, the name scientists give to the explosion produced when two neutron stars merge. It glowed blue at first, then shifted to red over the following days as different elements expanded outward through the debris cloud. This was the first time in history that humans had detected the same cosmic event using both gravitational waves and light. Scientists called it multi-messenger astronomy, meaning they had received two completely different kinds of signals from the same source at the same time. It was like hearing a sound and seeing the flash of light from the same event, but across 130 million light years of space. The discovery confirmed something scientists had long believed, but never proven. Neutron star collisions are one of the main places in the universe where heavy elements are made. The kilonova in NGC 4993 produced an estimated amount of gold equal to several times the mass of our Earth. That gold was scattered into space, where it will eventually mix with gas clouds, collapse into new solar systems, and perhaps one day settle onto the surface of a new planet. The gold in a wedding ring, the platinum in a laboratory instrument, the silver in an old photograph. All of it traces back to moments like this one. The scientists who built LIGO spent decades working toward that detection. The project began in the 1990s. Early versions of the detector were not sensitive enough. Engineers redesigned the mirrors, improved the lasers, isolated the equipment from vibrations, as small as ocean waves crashing on distant shores. The upgraded version, called Advanced LIGO, came online in 2015. Within its first few months, it detected gravitational waves for the very first time from two colliding black holes. The team behind that discovery received the Nobel Prize in Physics in 2017. The same year, the neutron star collision was observed. There is something deeply moving about what LIGO represents. It is a machine built to hear the universe, not with sound, but with the gentle stretching of space itself. And it worked. Human beings, standing on a small planet in an ordinary galaxy, built an instrument sensitive enough to feel the collision of two dead stars 130 million light years away. The pulsars pulse on in the dark. But sometimes, after 1 billion years of circling, two of them reach out and find each other. And when they do, the universe makes gold. Not every star that dies becomes a neutron star. Some stars are so massive, so heavy, that even the crushing density of a neutron star cannot hold them. When these giants collapse, nothing stops the fall. The core keeps shrinking past the point where neutron stars form. It shrinks past every known boundary. And what remains is something that bends the rules of physics in ways that still make scientists pause. A black hole is born. The idea of a black hole sounds like science fiction. A place where gravity is so strong that not even light can escape. But black holes are not fiction. They are a natural outcome of the universe's own laws. When a star more than about 20 times the mass of our sun runs out of fuel and collapses, the math leads to only one result. The gravity becomes so intense that space itself curves inward, sealing off a region from the rest of the universe. What was once a blazing star becomes a point of infinite density called a singularity, wrapped inside an invisible boundary called the event horizon. The event horizon is not a surface you could touch or see. It is more like a point of no return. Cross it, and nothing comes back. Not light, not information, not anything. From the outside, the black hole looks like a perfectly dark circle, a hole cut in the fabric of space. The region around it, though, can glow brilliantly. gas and dust falling toward the black hole heat up to millions of degrees. They spiral inward in a flat, glowing disk called an accretion disk. Some of the most luminous objects in the universe are black holes actively feeding, surrounded by rings of superheated matter shining brighter than entire galaxies. Here is something that surprises many people. The black hole itself does not pull any harder than the star that made it. If our sun somehow collapsed into a black hole, Earth would keep orbiting in exactly the same path. The gravity at a given distance stays the same. What changes is that you can now get much closer to the center than you ever could before. The surface of the sun kept you at a safe distance. The black hole has no surface. You can approach the center directly, and the closer you get, the stronger the pull becomes. The smallest stellar black holes, the ones born from collapsing stars, are called stellar mass black holes. They typically weigh between 5 and a few dozen times the mass of our sun. That might sound enormous, but in cosmic terms, these are the modest ones. The Milky Way galaxy alone may contain hundreds of millions of stellar mass black holes, most of them dark and silent, drifting through space without any nearby gas to reveal them. They are invisible unless something comes close enough to fall in. One of the strangest facts about black holes is that time behaves differently near them. This is not a metaphor. Einstein's theory of general relativity, which describes how gravity warps space and time, predicts that clocks run slower in stronger gravitational fields. Near the event horizon of a black hole, time slows dramatically compared to clocks far away. An observer falling toward a black hole would not notice anything unusual about their own clock. But someone watching from a safe distance would see that falling observer slow down, freeze, and fade, never quite crossing the horizon from the outside perspective. The universe plays strange games near these objects. Black holes also do not last forever, though their lifespans are almost impossible to imagine. A physicist named Stephen Hawking showed in 1974 that black holes slowly lose energy through a process now called Hawking radiation. Quantum effects near the event horizon allow tiny amounts of energy to leak away over time. For a stellar mass black hole, this process takes longer than the current age of the universe, many times over. These objects are, for all practical purposes, permanent. But the universe is patient. Given enough time, even a black hole fades. What strikes scientists most is how cleanly black holes emerge from the same process that scatters light and elements across the galaxy. A supernova can, in the same moment, seed nearby clouds with the raw material for new planets, and leave behind an object so extreme that it breaks our everyday understanding of space and time. The death of a massive star does not produce just one thing. It produces a shockwave, a glowing remnant, new atoms drifting outward, and sometimes, at the very center, a darkness so completed bends the universe around itself. Two outcomes born from the same collapse, pointing in completely opposite directions. One reaches outward, one folds inward, and both are part of how the cosmos renews itself. Those new atoms drifting outward, that phrase deserves a closer look. Because what a supernova scatters into space is not just debris. It is a precise collection of elements, each one forged under conditions so extreme that nothing else in the universe can make them. The explosion is not random. It is, in its own way, a kind of chemistry. A violent, brilliant chemistry that connects the death of one star to the birth of almost everything else. To understand this, it helps to start at the beginning of a star's life. For most of its existence, a star fuses hydrogen into helium deep in its core. That process releases the light and heat that keeps the star shining. But as the star ages, it begins fusing heavier and heavier elements. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes neon, then magnesium, then silicon. Each step requires higher temperatures and greater pressure. Each step produces a heavier atom. By the time a massive star reaches the end of its life, its core has built up a thick layer of iron. Iron is where the chain stops. A star cannot fuse iron to release energy. Iron absorbs energy instead of giving it off. So the core collapses and the explosion begins. But in those final seconds of collapse, and in the fierce heat of the shockwave that follows, something remarkable happens. Atoms are slammed together with such force that they fuse in ways that were never possible during the star's normal life. Elements heavier than iron begin to form. Gold, silver, platinum, uranium. These are not made in the quiet burning of a star. They are made in the chaos of its death. Scientists call this process the R process, which stands for rapid neutron capture. Free neutrons flood the collapsing core and slam into existing atomic nuclei faster than those nuclei can decay. In a fraction of a second, atoms are built up into forms that would take millions of years to produce any other way. The shockwave then carries these new atoms outward into space. A single supernova can produce more gold than the entire mass of the Earth, scattered across light years of open space. This is not a small detail. It is one of the most important connections in all of science. Every piece of gold ever mined on Earth came from an explosion like this. Every silver ring, every platinum wire in a laboratory, every gram of uranium sitting in a reactor, all of it was forged in the death of a star that lived and died long before our sun was born. These atoms drifted through space for millions of years. Then gravity pulled them into the cloud that would become our solar system. They settled into the forming Earth. And eventually, human hands pulled them from the ground, not knowing where they truly came from. The lighter elements have their own story. Carbon, oxygen, and nitrogen. The elements that form the backbone of all living things were made in the cores of stars and then released by supernova explosions. Without that release, they would stay locked inside the dead star forever. The explosion is what sets them free. It is what allows them to drift into new clouds, collapse into new stars, and eventually settle onto the surfaces of new worlds. Life, as we know it, depends on that release. Calcium, the element that makes bones hard, is produced in large quantities during a supernova. So is sulfur, which plays a role in proteins. So is phosphorus, which carries energy inside every living cell. These are not poetic connections. They are chemical ones. The atoms in a living body were processed through the heart of a dying star. That is simply what the evidence shows. What makes this so striking is the precision of it. The universe does not produce all elements equally. It produces them in specific ratios, through specific processes, at specific moments. Supernovae are one of the primary factories. Neutron star collisions, which were covered in an earlier part of this episode, are another. Together, these violent events fill the galaxy with the raw ingredients that planets and life require. Each explosion is not an ending. It is a delivery, a slow, spreading gift of matter that will eventually find its way into something new. The atoms in your body were not always yours. They belonged to a star once. That star burned for millions of years, built those atoms layer by layer in its core, and then gave them away in a single blinding moment. They traveled across space. They became part of the Earth, and now, quietly, they are part of you. The universe has been building toward this for a very long time. The early universe was almost empty. Not empty in the way a quiet room is empty. Empty in a deeper way. When the universe was very young, just a few minutes old, it contained almost nothing but hydrogen and helium. These are the two simplest elements. Hydrogen has one proton. Helium has two. That was nearly everything. The periodic table, with all its variety and richness, did not yet exist. Carbon, oxygen, iron, gold, none of it was there. The universe had to build those things. And supernovae were one of the primary tools it used. The first stars formed about 100 million years after the Big Bang. Scientists call these the population III stars. They were enormous, far larger than most stars that exist today. Because they contained only hydrogen and helium, they burned through their fuel very quickly. A star that massive lives fast and dies young. Many of them lasted only a few million years before they collapsed and exploded in some of the most powerful supernovae the universe has ever seen. These were not small events. Some of them may have been what scientists call hypernova, explosions many times more energetic than a standard supernova. When they went off, they scattered the first heavy elements into the surrounding gas. That gas was changed forever. Before those first explosions, it was simple. After them, it was seeded with carbon, oxygen, nitrogen, and other elements that had been forged in those massive stellar cores. The gas clouds that formed next, the ones that collapsed into the second generation of stars, were already richer. They contained more variety. And when those second generation stars eventually exploded, they added even more elements to the mix. Each wave of stellar birth and death made the universe more complex, more capable of building something new. This process is called chemical enrichment. It is slow. It happens over hundreds of millions of years, but it is relentless. Every generation of stars takes what the previous generation left behind and builds on it. The universe has been doing this for nearly 14 billion years. What started as a sea of hydrogen and helium has become a galaxy full of iron, calcium, sulfur, silicon, and dozens of other elements, all of it built up layer by layer, explosion by explosion, across deep time. The early universe was also much smaller and denser than it is today. Galaxies were closer together. Gas clouds were more tightly packed. This meant that the material scattered by early supernovae did not have to travel as far before it was swept up into new stars and new systems. The enrichment happened quickly by cosmic standards. Within the first few billion years, the universe had already produced enough heavy elements to begin forming rocky planets. Earth-like worlds became possible. Before supernovae seeded the early universe, they were not. Scientists study this history by looking at very old stars, stars that formed early in the universe's life, still carry the chemical signature of that time. They contain very small amounts of heavy elements compared to younger stars like our sun. By measuring those ratios, scientists can read the history of enrichment like a record written in light. Each star is a kind of time capsule. Its chemistry tells us what the universe looked like when it was born. And the process is still going on. The universe is still changing. Stars are still forming, burning, and dying. Supernovae are still happening across the galaxy and across billions of other galaxies. Each one adds to the total inventory of elements drifting through space. The universe today is richer in heavy elements than it was 1 billion years ago. 1 billion years from now, it will be richer still. The slow accumulation never stops. What is remarkable is how patient this process is. No single explosion changes everything. But across millions of explosions, spread across billions of years, the universe transforms itself completely. It starts with almost nothing and builds, through fire and collapse and scattering, toward something far more complex, toward worlds, toward oceans, toward living things made of dozens of different elements, all of them forged in stars. The early universe had no iron. It had no carbon. It had no way to build a cell or a shell or a leaf. Supernovae changed that. They did not do it quickly. They did it the way all deep change happens in the universe. Slowly, steadily, one explosion at a time, across a span of time so vast it is almost impossible to hold in the mind. But the result is here. You can see it. You are made of it. The universe built itself, piece by piece, out of its own beautiful wreckage. Think about the iron in your blood right now. It is there, moving through you, carrying oxygen from your lungs to every corner of your body. You were born with it. Your mother passed it to you. Her mother passed it to her. And if you trace that iron back far enough, past every human generation, past the formation of Earth itself, you arrive at a star that died in a violent explosion billions of years ago. The iron in your blood is stardust, not as a poetic idea, as a physical, chemical, measurable fact. Iron is one of the most common elements in the human body. An adult carries roughly 4 grams of it, mostly inside red blood cells. Those cells use iron to hold onto oxygen molecules and carry them through the bloodstream. Without iron, that process fails. The body cannot breathe properly at the cellular level. Iron is not optional. It is foundational. And every atom of it was forged inside a dying star. Stars produce iron through a process called nuclear fusion, where lighter elements are pressed together under enormous heat and pressure to form heavier ones. For most of a star's life, fusion releases energy. It pushes outward and keeps the star from collapsing under its own gravity. But iron is different. When a massive star begins fusing iron in its core, the process absorbs energy instead of releasing it. The star loses its ability to hold itself up. Iron is the element that ends a star's life. It is the last thing a star makes before it falls apart. When the star collapses and then explodes as a supernova, it blasts that iron outward into space. The explosion scatters it across light years, mixing it with hydrogen clouds and the remnants of older stars. Over millions of years, gravity pulls those clouds together into new stars and new planetary systems. Some of that iron settles into rocky planets. Some of it ends up in the oceans. Some of it eventually ends up inside living cells. Light tells this story in a way nothing else can. When astronomers point a spectrograph at a glowing supernova remnant, the light coming back is not a single color. It is a pattern of colors, each one tied to a specific element. Iron glows with its own signature. So does calcium. So does silicon and sulfur and nickel. Every element emits light at particular wavelengths, like a fingerprint made of color. Scientists can read those fingerprints and know exactly what a cloud of gas is made of, even from thousands of light years away. The Cassiopeia, a supernova remnant, glows in X-ray light with brilliant oranges and greens and blues, each color marking a different element scattered by the explosion. Iron appears in the outer rings of the remnant, thrown far from the core. Silicon and sulfur glow closer in. The image looks like a piece of stained glass lit from behind. But every color is a chemical signature, a record of what the star made before it died. Light is the language the universe uses to tell us what it is made of. The calcium in your bones carries the same story. Supernovae produced it. So did the oxygen in every breath you take, the carbon in every cell of your body, the phosphorus in your DNA. These are not trace amounts. They are the main ingredients. The human body is built almost entirely from elements that stars made and supernovae scattered. You are not just connected to the stars in some distant, abstract way. You are assembled from them, atom by atom. There is something deeply settling about this. The universe is not separate from the life it contains. It did not create life as an afterthought. It built the ingredients slowly over billions of years through the lives and deaths of countless stars. Each explosion was a kind of generosity, though the universe has no intentions. It simply follows its own laws, and those laws, followed patiently across vast stretches of time, produced iron and carbon and calcium, and eventually the conditions for something to live. When you look at your own hand, you are looking at the end product of billions of years of stellar chemistry, the light that lets you see it bounced off atoms that were once inside a star. The iron that keeps you alive was forged in a core that collapsed in an instant and exploded with the brightness of a billion suns. That explosion happened long before Earth existed, but its result is here, warm and living, breathing quietly in the dark. The universe made you out of what it had, and what it had, it made in fire. After the fire comes the quiet. After the explosion fades, after the light dims across the galaxy, something remains. A cloud of gas and dust and glowing debris, slowly spreading outward through space. Scientists call it a supernova remnant. It is the ghost of a star, still moving, still shining, still carrying the energy of the moment it died. These remnants are not dark. They glow. The gas inside them is so hot and so energized that it radiates light across many wavelengths, including X-rays, radio waves, and visible light. Some of the most beautiful structures ever photographed in space are supernova remnants. They billow outward in great curling sheets of color, reds and blues and golds, lit from within by the energy of the original blast. The Crab Nebula is perhaps the most famous of these glowing clouds. It sits about 6,500 light years from Earth in the constellation Taurus. Chinese astronomers recorded the explosion that created it in the year 1054. They wrote that a new star appeared in the daytime sky, bright enough to see even in sunlight, for nearly a month. What they witnessed was a supernova. What remains today is a cloud roughly 11 light years across, still expanding outward at about 1,500 kilometers per second. At the center of that cloud spins a pulsar, a rapidly rotating neutron star, flashing 30 times every second, like a tiny, furious lighthouse. The Crab Nebula has been studied more than almost any other object in the sky. pulses in X-rays, in radio waves, invisible light. Scientists use it as a kind of calibration tool, a known, steady source of energy against which they can measure other things. In that way, the death of a star became a gift to astronomy. Now here is something remarkable. Space is a vacuum. Sound cannot travel through a vacuum the way it travels through air. There are no molecules to carry a pressure wave from one place to another across the open void. And yet, inside the dense gas clouds of supernova remnants, pressure waves do exist. Vibrations move through the hot plasma, the electrically charged gas, in ways that behave something like sound. NASA scientists have taken data from the Chandra X-ray Observatory, a space telescope that detects X-ray light, and converted those pressure waves into actual audio. They mapped the variations in the gas, translated them into frequencies a human ear can hear, and played them back. The result is haunting. The Cassiopeia A remnant, one of the youngest known supernova remnants in our galaxy, produces a deep, low rumble when its data is converted to sound. It is not a melody. It is something more elemental than that. A slow, resonant drone, like the lowest note of a massive pipe organ held down in a dark room. Scientists call this process sonification, turning astronomical data into sound, so that both researchers and the public can experience the universe in a new way. Cassiopeia A itself is extraordinary. The star that created it exploded roughly 340 years ago. Though the light from that explosion reached Earth around 1680, it sits about 11,000 light years away. The remnant is now about 10 light years across and still expanding. It glows brilliantly in X-rays, and the Chandra telescope has mapped it in stunning detail, revealing knots and filaments of gas, regions where the shockwave is slamming into surrounding material and heating it to millions of degrees. That shockwave is still doing work. As it pushes outward, it compresses the gas it encounters. That compression heats the gas. The heated gas glows. And in that glow, astronomers can read the chemical fingerprints of what the star was made of. They can detect silicon, sulfur, calcium, iron, all the elements forged in the star's core and scattered by the explosion. The remnant is a kind of record, written in light, of everything the star built during its long life. Some remnants last for tens of thousands of years before they finally fade and blend into the surrounding gas of the galaxy. During that entire time, they are slowly mixing their contents into the space around them. The elements they carry spread outward. They cool, they drift. Eventually, they join the great clouds of gas and dust that float between the stars, waiting for the right conditions to collapse and form something new. Every glowing remnant is an ending that is also a beginning. The cloud expands. The light slowly dims. The atoms scatter. And somewhere, perhaps millions of years later, some of those same atoms find each other again in a new cloud, drawn together by gravity, beginning the long, slow process of becoming a star. Those scattered atoms do not drift forever without purpose. The universe keeps careful accounts, and the numbers behind how supernovae shape entire galaxies are, in their own quiet way, as beautiful as anything you can see in the night sky. A single supernova releases an almost impossible amount of energy. In just a few seconds, it pours out roughly 10 to the power of 44 joules of energy. That number is so large, it barely fits in the human mind. To put it gently into scale, our sun will release that same amount of energy, but spread across its entire 10 billion year life. A supernova does it in a breath. Most of that energy, about 90% of it, leaves not as light, but as neutrinos, tiny, near-weightless particles that pass through almost everything. The remaining 10% still represents more energy than the sun will ever produce, and a small fraction of that becomes the shockwave, the light, the heat, and the scattered elements that reshape everything around them. Galaxies are not static. They breathe. They cycle their gas through a long, slow process of birth, death, and renewal. Supernovae are one of the main engines driving that cycle. When a supernova explodes, it does not just scatter elements outward. It pushes the surrounding gas with tremendous force, carving out enormous bubbles of hot, thin gas inside the galaxy. These bubbles, sometimes called superbubbles, when many supernovae explode close together, can stretch for hundreds of light years across. 1 light year is about 9.5 trillion kilometers. These bubbles are not small. The energy from supernovae can push gas not just sideways through a galaxy, but upward and outward, away from the flat disk where most stars live. Astronomers call this a galactic wind, a slow outward flow of gas driven by the combined pressure of many stellar explosions over millions of years. In galaxies that are forming stars very rapidly, these winds can carry enormous amounts of gas away from the galaxy entirely. That gas is lost, at least for a while. It changes how many new stars the galaxy can form. In this way, supernovae act as a kind of regulator, slowing star formation when it gets too intense, keeping the galaxy from burning through all its fuel too quickly. The numbers that govern this regulation are elegant in their simplicity. Astronomers estimate that in a galaxy like our own Milky Way, a supernova occurs roughly once or twice every century. That rate is enough to stir the gas, drive the winds, and keep the galaxy cycling without overwhelming it. Too many supernovae too quickly, and the galaxy blows away too much of its own material. Too few, and the gas collapses too fast, forming stars in a great rush that exhausts the supply. The rate we observe sits in a kind of natural balance, steady and self-correcting over billions of years. There is a ratio that appears again and again in this story. The fraction of a galaxy's gas that gets converted into stars each year is very small, typically around 1 to 2% of the available material. Supernovae help keep that number low and steady. Without their feedback, models suggest that galaxies would have turned most of their gas into stars very early in the universe's history, leaving little material for later generations. The stars we see today, including our own sun, exist in part because earlier supernovae slowed the process down. The explosion of one star made room for another. On the largest scales, supernovae also help distribute heavy elements across enormous distances. The iron, calcium, and oxygen forged in stellar cores do not stay close to where they were made. Galactic winds carry them far out into the space between galaxies. into what astronomers call the intergalactic medium, the vast, thin gas that fills the spaces between island universes. Observations show that even this remote, nearly empty space contains metals, elements heavier than hydrogen and helium, that could only have come from stars. Supernovae carried them there. The reach of a single stellar explosion, traced through the math of fluid dynamics and gravity and pressure, extends across millions of light years. The universe runs on rules: pressure, gravity, energy, time. These forces do not negotiate. They simply act, and the result, worked out over billions of years, is a galaxy that sustains itself, that recycles its material, that builds new stars from the wreckage of old ones. The numbers are not cold. They describe something living. A galaxy is not a collection of separate objects. It is one connected system, and supernovae are among the forces that hold that system in its long, slow, steady balance. That balance is fragile. It is not fragile in the way a glass is fragile, something that shatters with one wrong move. It is fragile the way a flame is fragile, steady and bright as long as the right conditions hold, but dependent on more than it appears. Think about what it takes to make a new star. You need a cloud of gas and dust, cold and dark, and spread across many light years. You need that cloud to begin pulling itself together under its own gravity. But here is the quiet problem. Cold gas clouds resist collapse. The pressure inside them pushes outward. Gravity pulls inward. For a very long time, these two forces hold each other still. Nothing happens. The cloud just drifts. Then, a supernova shockwave arrives. The shockwave from a dying star can travel outward at speeds of tens of thousands of kilometers per second. When it reaches a cold gas cloud, it does something precise. It compresses the outer edge of the cloud. It squeezes the gas just enough to tip the balance. Gravity, which had been held in check, suddenly wins. The cloud begins to fall inward. A new star is born. Scientists call this process triggered star formation. The word triggered is exactly right. The supernova does not build the new star. It simply releases a process that was already waiting. The raw material was always there. The gravity was always there. What was missing was a push, and a dying star, in its final violent act, provides exactly that push. This is one of the most delicate things in the universe. The shockwave must be strong enough to compress the cloud, but not so strong that it tears the cloud apart entirely. If the explosion is too close, the gas scatters. If it is too far away, the shockwave loses too much energy before it arrives, and the cloud does not respond. There is a range, a narrow band of distance and energy, where the outcome is a new star rather than scattered debris. The universe threads this needle constantly, across billions of years, across billions of star-forming regions. Our own solar system may owe its existence to exactly this kind of trigger. Evidence found inside ancient meteorites, the oldest solid objects in our solar system, shows traces of aluminum-26, a radioactive element that decays quickly and must have been made in a nearby supernova shortly before our sun formed. The timing is striking. Scientists believe a supernova exploded close to the cloud of gas that would become our sun, and that explosion compressed the cloud and started the collapse. The sun, the earth, the moon, every planet in this system may have been triggered into existence by a star that died before our sun was even born. That star left no remnant we can see. Its name, if it had one, is lost, but its shockwave reached a quiet cloud of gas at exactly the right moment, with exactly the right force, and set in motion a chain of events that eventually produced this planet, and the oceans on it, and the life in those oceans, and every living thing that has ever breathed air beneath an open sky. The conditions that followed were no less precise. Earth formed at a distance from the sun where liquid water can exist on the surface, not too hot, not too cold. That distance is sometimes called the habitable zone, the narrow band around a star where temperatures allow for liquid water. Move Earth just a little closer to the sun, and the oceans boil away. Move it just a little farther, and they freeze solid. The difference between those outcomes is not enormous. It is a matter of a few percent in orbital distance. The atmosphere adds another layer of precision. Earth's thin blanket of air, just a narrow shell compared to the size of the planet, blocks harmful radiation from space, holds in warmth, and carries the oxygen that breathing creatures need. Without it, the surface would be cold and bare and silent. With too much of it, the heat would build until the surface became uninhabitable. The balance is exact, and it is maintained by systems that connect to one another. The carbon cycle, the water cycle, the movement of tectonic plates, the presence of a large moon that steadies Earth's tilt. All of this traces back, in one way or another, to the stars that lived and died before our sun was born. The supernova that may have triggered our solar system's formation was not an ending. It was a beginning. The universe does not waste its energy. It redirects it quietly, precisely, across distances and timescales too large to fully imagine, toward outcomes that feel, against all odds, exactly right. There is one kind of supernova that changed everything we thought we knew about the universe. Not because of what it destroys, because of what it measures. It is called a type Ia supernova. It happens in a binary system, two stars orbiting each other in a slow, close dance. One of those stars has already died. It has collapsed into a white dwarf, a dense, dim ember roughly the size of Earth, but carrying the mass of an entire sun. The other star is still alive, still burning, still swelling with age. And slowly, the white dwarf begins to pull material from its companion, drawing hydrogen and helium across the space between them like a quiet, patient thief. This continues for a very long time. The white dwarf grows heavier. It gains mass little by little, year by year, century by century. And then it reaches a limit. Scientists call this the Chandrasekhar limit, named after the physicist Subramanian Chandrasekhar, who calculated it in 1930. It sits at about 1.4 times the mass of our sun. When a white dwarf reaches that exact threshold, it can no longer hold itself together. Carbon fusion ignites through the entire star at once. The explosion is total. Nothing survives. What makes this remarkable is the word exact. Every type Ia supernova explodes at nearly the same mass. That means every type Ia supernova releases nearly the same amount of energy. And that means every type Ia supernova reaches nearly the same peak brightness. Scientists call objects like this standard candles. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. Type Ia supernovae became the most precise measuring sticks in all of astronomy. In the 1990s, 2 teams of scientists used these measuring sticks to study the distant universe. They expected to find that the universe was expanding, but slowing down. Gravity, after all, pulls things together. The explosion of the Big Bang had sent everything flying outward. But over billions of years, that expansion should have been losing speed. The scientists expected to confirm this. They did not. What they found instead stopped them cold. The distant supernovae were dimmer than they should have been. Not by much, but by enough. The universe was not slowing down. It was speeding up. Something was pushing galaxies apart faster and faster, working against gravity across the entire span of space. Scientists gave this force a name: dark energy. The name is honest about what we do not know. It is dark because we cannot see it. It is energy because it appears to be driving the expansion of space itself, and it makes up roughly 68% of everything in the universe. That number sits at the center of one of the deepest unsolved questions in all of science. We do not know what dark energy is. We do not know where it comes from. We do not know if it is constant, a fixed property of space itself, or if it changes over time. Some scientists think it may be a property built into the fabric of space, something Einstein called the cosmological constant. Others think it may be something stranger, a field that shifts and evolves as the universe ages. The measurements from type Ia supernovae are what told us it exists at all. And those same measurements are now being refined, checked, and challenged by new telescopes and new methods, because the answer matters enormously. There is even a tension in the data, different ways of measuring how fast the universe is expanding give slightly different answers. This disagreement is called the Hubble tension, named after Edwin Hubble, the astronomer who first measured the expansion of the universe nearly a century ago. Some scientists think it is a measurement error. Others think it may point toward something new in physics, something we have not yet imagined. The debate is ongoing, careful, and alive. This is what makes science feel so much like the universe itself. It keeps opening. Every answer uncovers a deeper question. The white dwarf that quietly steals mass from its neighbor. The explosion that briefly outshines a galaxy. The faint dimness of a distant light measured by a careful human eye. All of it leads here to a mystery written into the structure of space, still waiting to be read. The universe is not finished telling us what it is, and the fact that a dying star, collapsing at a precise and predictable mass, became the instrument we used to discover that mystery, feels like exactly the kind of quiet, unlikely connection that runs through everything. Right now, as you rest, telescopes around the world are watching stars they know will explode. Not in a moment of panic or urgency, but with the patient, steady attention of people who understand that the universe moves on its own schedule. Some of these stars have been under observation for decades. Scientists track their brightness, their temperature, their swelling size. They are waiting calmly and carefully for the moment when one of them finally lets go. One of the most watched stars in the sky is Betelgeuse. It sits in the shoulder of the constellation Orion, glowing with a deep red-orange light that you can see on any clear winter night. Betelgeuse is a red supergiant, a star so enormous that if it replaced our sun, its surface would stretch past the orbit of Jupiter. Stars this large burn fast and die young, and Betelgeuse is already old. Astronomers believe it is nearing the end of its life, though nearing in stellar terms could still mean 100,000 years from now. In late 2019, Betelgeuse did something unusual. It dimmed, noticeably, measurably, in a way that caught the attention of astronomers everywhere. For a few months, it faded to about a third of its normal brightness. Some wondered if this was a sign that the end was close. Later research suggested the dimming was caused by a large cloud of dust the star had thrown off from its own surface, temporarily blocking its light. The star was not collapsing. It was simply doing what old, restless giant stars do. It was changing, but the episode reminded everyone watching that Betelgeuse is not a stable, quiet star. It is active, variable, and unpredictable. It is a star in its final chapter. There is another star that astronomers watch with particular care. It is called Eta Carinae, and it sits much farther away, about 7,500 light years from Earth. Eta Carinae is one of the most massive and luminous stars known to exist in our galaxy. It is so bright that it radiates about 5 million times more energy than our sun. In the 1840s, it went through a violent eruption that made it briefly the second brightest star in the night sky, even though it was thousands of light years away. That eruption released as much energy as most supernovae, yet the star survived. It threw off enormous shells of gas and dust that are still expanding outward today, glowing in beautiful curved arcs of orange and gold when seen through a telescope. Astronomers believe Eta Carinae is a strong candidate for a future supernova, though again, the timing is uncertain. It could be tomorrow on a cosmic scale, or it could be far beyond any human lifetime, beyond our own galaxy. Astronomers are watching supernovae happen in real time. Every year, surveys of the sky detect hundreds of supernovae in distant galaxies. Wide-field telescopes scan the night sky automatically, comparing new images to old ones, looking for any star that has suddenly grown much brighter. When they find one, alerts go out within minutes to observatories around the world. Astronomers then turn their best instruments toward that point of light and begin collecting data immediately, capturing the full arc of the explosion as it unfolds over days and weeks. One remarkable example came in 1987 when a supernova exploded in the Large Magellanic Cloud, a small galaxy that orbits our own Milky Way. It was close enough, only about 160,000 light years away, that scientists could study it in extraordinary detail. They detected the burst of neutrinos that arrived hours before the visible light, confirming long-held theories about how the core collapses. Astronomers have been watching the remnant of that explosion, called SN 1987A, ever since. The glowing ring of gas around it continues to brighten as the shockwave from the explosion slams into material the star shed long before it died. It is a slow, luminous collision, and it is still happening right now. This is what makes the present moment in astronomy feel so alive. We are not only looking back at what stars have done, we are watching them do it. The tools we have built, the satellites, the ground-based observatories, the automated sky surveys running through the night, have turned the whole sky into something we can monitor together. Every new supernova detected in a distant galaxy is a data point. Every one teaches us something, and somewhere out there, in a galaxy we may or may not be able to see with the naked eye, a star is collapsing right now, sending its light racing toward us, a message we have not yet received, but one that is already on its way. And some of that light may not have far to travel at all. There are stars in our own galaxy, stars close enough to see on a clear night that scientists believe could explode within the next 100,000 years. That sounds like a long time, but in the life of the universe, it is barely a breath. These stars are already old, already burning through their last reserves, already moving slowly and inevitably toward the moment when gravity wins. One of the most watched is Betelgeuse. It sits in the shoulder of the constellation Orion, and on any winter night in the northern hemisphere, you can find it glowing with a deep reddish-orange light. That color tells you something important. Betelgeuse is a red supergiant, a star so enormous that if you placed it where our sun sits, its outer edge would swallow Mercury, Venus, Earth, and Mars. It would reach nearly to Jupiter. It is almost too large to picture. Betelgeuse is also unstable. It pulses. It dims and brightens in irregular cycles, and astronomers have been watching it closely for years. In late 2019 and early 2020, it dimmed dramatically. Scientists called it the Great Dimming. Some wondered if the end was near. Evidence later suggested the star had released a massive burst of gas and dust that briefly blocked some of its light. It was not the final collapse, but it was a reminder. This star is restless. It is not done surprising us. When Betelgeuse does finally explode, the view from Earth will be extraordinary. Scientists estimate it will shine brighter than the full moon. It may be visible in the daytime sky for weeks. It will cast faint shadows at night, and then, slowly, over months and years, it will fade. It will leave behind a glowing cloud of gas and debris, a new nebula drifting through the Milky Way, seeding the space around it with the elements it spent millions of years building inside its core. Betelgeuse sits roughly 700 light-years away. That is far enough that its explosion poses no threat to Earth. The dangerous range for a supernova, the distance at which the radiation could seriously affect our atmosphere, is thought to be somewhere around 25 to 50 light-years. No known candidate star sits that close. We are, as far as scientists can tell, safely out of reach. But there are other stars worth watching. Eta Carinae is one of the most massive and luminous stars known in the Milky Way. It sits about 7,500 light-years away, which again puts us well beyond harm. But its sheer energy is staggering. In the 1840s, it erupted in what astronomers call a hypernova imposter event, a massive outburst that made it briefly the second brightest star in the sky without actually destroying it. It shed enormous amounts of mass. Today, that expelled material forms a glowing double-lobed cloud called the Homunculus Nebula, visible through telescopes as a golden, dusty shell surrounding the star. Eta Carinae is thought to be near the end of its life. When it finally goes, it may produce one of the most energetic explosions our galaxy has seen in recorded human history. There is something quietly moving about knowing these stars by name. Betelgeuse, Eta Carinae, Antares, another red supergiant glowing in the heart of Scorpius, also thought to be in its final stages. These are not abstract objects in a textbook. They are lights you can step outside and see tonight. They have been burning since before humans walked the earth, and some of them will end in fire that we, or our descendants, will witness with their own eyes. Every one of those future explosions will do what every supernova before them has done. They will scatter their contents into the galaxy. Carbon, oxygen, silicon, iron, gold, the raw material of planets, of oceans, of living things. The atoms that make up your body were forged in stars that died long before our sun was born. You are, in the most literal sense, made of ancient stellar fire. That connection runs in both directions. We look up at Betelgeuse, and we see a star approaching its end. But we are also, in a way, looking at our own beginning. The same process that will one day tear that star apart is the process that built us. The same forces, the same elements, the same physics, playing out across billions of years and billions of light years, arriving here in this moment in you. The universe is not a cold and empty place. It is generous. It has been building toward life for a very long time. And so we come to the end of this long, quiet night of wonders. We have traveled far together. From the first breath of a young star to the final collapse of a dying one. From the blinding flash of a supernova to the slow, glowing clouds it leaves behind. From the iron in your blood to the gold in the ground beneath your feet. All of it connected. All of it part of one long, unfolding story that began nearly 14 billion years ago and is still being written tonight. The next supernova in our galaxy is coming. Scientists believe it happens roughly once or twice every century across the Milky Way, though the last one visible to the naked eye was in 1604. That star exploded over 400 years ago, and we have been waiting ever since. When the next one comes, it will be the most studied explosion in human history. Every telescope on Earth and in orbit will turn toward it. Every detector, every satellite, every instrument we have ever built will listen. And they will hear something extraordinary. Before the light even arrives, the neutrinos will come. Neutrinos are tiny, nearly massless particles that pass through almost everything without stopping. A supernova sends out more energy in neutrinos in a single second than our sun will release in its entire 10 billion year life. Those neutrinos travel at nearly the speed of light. They will reach us hours before the visible light does, giving scientists a precious early warning that a star has just died. We know this because it already happened once. In 1987, a star exploded in a small galaxy near the Milky Way called the Large Magellanic Cloud. It was the closest supernova seen in nearly 4 centuries. Detectors buried deep underground in Japan, the United States, and Russia all caught a burst of neutrinos arriving just before the light. 19 tiny particles. That is all. But those 19 particles confirmed a theory that physicists had held for decades. The core of a dying star really does collapse. The bounce really does happen. The physics really does work the way we thought. The next galactic supernova will give us thousands of neutrinos, maybe tens of thousands. It will be a flood of information. Scientists will be able to map the interior of a collapsing star in real time, watching the core squeeze down in the final moments before the shockwave tears everything apart. We will learn things about matter under extreme pressure that no laboratory on Earth can replicate. We will also learn about gravity. When neutron stars form, they send ripples through the fabric of space itself. These are called gravitational waves, and detectors like LIGO can sense them. A nearby supernova would produce gravitational waves strong enough to study in detail. Combined with the neutrino signal and the light, scientists would have 3 completely different ways of watching the same event at once. That has never happened before, not at that scale. And all of that learning will come from something that, to the universe, is simply ordinary. Stars have been doing this for billions of years, long before Earth existed, long before the sun ignited. The galaxy has been seeding itself with the products of these explosions since the very first massive stars burned out in the early universe. Every supernova that ever happened helped build the world you live in now. That is worth sitting with for a moment. Right now, somewhere in the Milky Way, a massive star is in its final years. It does not know. It simply burns as it always has, fusing heavier and heavier elements in its core, moving toward the iron that will end it. And when that moment comes, the energy released will be staggering. The light will cross the galaxy. The neutrinos will arrive first, and somewhere on a small blue planet orbiting an ordinary star, people will look up and see something new and bright in the sky, and they will understand, in a way no generation before them fully could, exactly what they are seeing. They will be watching the universe make something new. Out outside tonight, the sky is full of stars. The galaxy turns slowly overhead, a slow wheel of ancient light. The oceans rest under the moon. The earth breathes in the dark, quiet and warm, carrying everything that billions of years of stellar fire made possible. You are part of all of it. Every atom, every breath, every moment of wonder you have ever felt. The universe built you out of the wreckage of stars, and it is still building. Rest now. The stars will keep watch. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.